This is series solutions of differential equations, and we are going to be talking about power series solutions to linear differential equations. Let's go ahead and begin by taking a look at our linear differential equation. We have a homogeneous linear differential equation, and let's go ahead and write that in standard form. So we will have y double prime plus, and let's go ahead and write p of x, and we will define what p of x is in a moment. And let's have q of x here multiplied by y is equal to 0. And we can see here that p of x is going to be equal to a1 of x divided by a2 of x. And we have q of x equal to a naught of x divided by a2 of x. With that, what we want to say is, and define is, what an ordinary and a singular point is. So a point x naught is called an ordinary point of equation 2, and this is going to be my equation 2. If both p of x and q of x are analytic at x naught. If x naught is not an ordinary point, it is called a singular point of the equation. So let's jump right in and look at this first example where we're going to be seeing if we can find the singular points of the differential equation. So in this first example, we'll go ahead and divide every term by x plus 1, and now we can clearly see that p of x is equal to the opposite of x squared over x plus 1, and we have q of x equal to 3 divided by x plus 1. So these functions are rational functions, and they are analytic everywhere except where their except at their zeros are of their denominator. So let's go ahead and set the denominator equal to 0, and of course we have x equal to -1. This is a point of discontinuity for both p of x and q of x. So therefore x equal to -1 is, and it's actually the only singular point of the differential equation. Okay, let's take a look at our next example. We have theta squared minus 2. We will divide every term by that factor. So we'll have y double prime plus 2 divided by theta squared minus 2, y prime plus the sine of theta divided by theta squared minus 2 multiplied by y is equal to 0. So our coefficients, p of x equal to 2 divided by theta squared minus 2, and we have q of x equal to the sine of theta divided by theta squared minus 2. So these are analytic everywhere except where they have their zeros. So the zeros of these rational functions. So we will have theta squared minus 2 equal to 0, theta squared equal to 2, and theta equals plus or minus root 2. So this differential equation has two singular points. So we will say the singular points are theta equal plus the square root of 2 and theta equal the opposite of the square root of 2. Okay, let's take a look at the next example. We're going to do the same thing. We're going to divide that coefficient, which is a quadratic, by every term by that. So we're going to have x double prime plus t plus 1 divided by t squared minus t minus 2, x prime minus t minus 2 times x is equal to 0. So as you can see, we have p of t equal to t plus 1 divided by t squared minus t minus 2. And we also have q of t equal to the opposite of t minus 2 divided by t squared minus t minus 2. Well, this is equal to t plus 1, of course, divided by t plus 1 multiplied by t minus 2. And we'll do the same thing over here. We have the opposite of t minus 2 divided by t plus 1, t minus 2. So the point t equal to -1 is actually a removable singularity for p of t, since t cannot be equal to -1. Now keep in mind, we have to look at both p of t and q of t. So let's talk about this a minute. The t plus 1 term can be canceled in p of t. So p of t is actually, let's make a note, p of t is analytic at t equal to -1 if we set p of -1 equal to, and we'll take that limit as t approaches -1 of p of t, and that's going to be the limit as t approaches -1 of 1 divided by t minus 2, and we can see that that's equal to 1/3. So at the point t equal to 2, we do have an infinite discontinuity. So p of t is analytic everywhere, so therefore p of t is analytic everywhere. You know what? I'm just going to go ahead and write this 1/3 over here so that I have a little bit more room. Except at t equal to 2. Okay, but now we need to look at q of t. Okay. So for q of t is analytic everywhere except at t equal to -1. So we can say in a similar fashion that q of t is analytic at t equal to +2 if q of 2 is equal to the limit as t approaches 2 of q of t, which will be the limit as t approaches 2 of 1 divided by t plus 1, which is going to be equal to, and actually I did forget a negative here, so this would be a negative 1/3. And so we can say, therefore, q of t is analytic everywhere except t equal to -1. So we put that together. So therefore, our differential equation has two singular points. And that would be t equal to -1 and t equal to 2. Okay, let's take a look at our next differential equation. We are looking for our singular points. So again, we will write our equation in the form dividing every term by the sine of x. So we have that p of x is identically equal to 0. And we have q of x. Of course, this is the cotan of x, but we have the cosine of x divided by the sine of x. Now, this is a quotient of two analytic functions. Both of these functions have power series expansions about any real number x with an infinite radius of convergence. So q of x has a power series expansion with positive radius of convergence about every real number as long as the sine of x is not equal to 0. So we do need to make sure that setting sine of x equal to 0, we get x is equal to n pi, and of course n is going to be 0 plus or minus 1, and so on and so forth. And these are the only singular points of the DE. So therefore, x equal to n pi, n equal to 0 plus or minus 1, and so forth, are the singular points of the equation. Okay, let's take a look at our next example. And we have y double prime minus x squared minus 1 over e to the xy prime plus 2x divided by e to the xy is equal to 0. So we have p of x equal to the opposite of x squared minus 1 over e to the x, and we have q of x equal to 2x over e to the x. So both p of x and q of x are quotients of analytic functions. Now we do need to make sure that that denominator is not equal to 0 to see if we have any points where it's 0. And of course, we do not have any since e to the x is not equal to 0 for all x. Therefore, there are no singular points. And we can say also e to the x is not equal to 0 for all x. Okay, let's look at our next example. So we have y double prime plus the sine of 2x divided by the natural log of x minus 1, y prime minus e to the x divided by the natural log of x minus 1, y is equal to 0. We can see here that we have p of x equal to the sine of 2x divided by the natural log of x minus 1, and we have q of x equal to the opposite of e to the x divided by the natural log of x minus 1. Now, we do have a quotient of analytic functions for both p of x and q of x. So p of x and q of x are analytic except where the natural log of x minus 1 is 0 or undefined. So, of course, we have the natural log of x minus 1. Whoops. We have that x minus 1 must be greater than 0. So x must be greater than 1. So this implies that we have a singular points on the interval from negative infinity to 1. And we also know that setting the natural log of x minus 1 equal to 0, of course, exponentiating both sides, we get x minus 1 is equal to 1, and we have x equal to 2. So we have singular points at x equal to 2 and every point on the interval from negative infinity to 1. Okay, moving on to our next example. Here we are going to find at least the first 4 non-zero terms in a power series expansion about x equal to 0 for a general solution to this differential equation. So first we see that x equal to 0 is an ordinary point for the equation. Let's go ahead and put since. So since that is true, then we seek a general solution. In the form, and this is what we will be using. So we are looking for the form W equals the sum from k equals 0 to infinity of a sub k multiplied by x to the k power. So what we're going to do is we're going to find the derivatives of W. Okay, so we have W prime is equal to the sum from k equal 1 to infinity of a sub k multiplied by k x to the k minus 1. And we have W double prime is equal to the sum from k equal 2 to infinity of a sub k multiplied by k minus 1 times x raised to the k minus 2 power. So we are going to take those and place them over here in our equation. So we have the second derivative, which is the sum from k equal 2 to infinity of a sub k times k minus 1, x to the k minus 2. I'm just going to make this a little bit smaller. And then we'll have a little bit more room. And now we have to subtract x squared multiplied by W prime. And so we have, and I actually think I'm going to put these here. I'll just go ahead and leave them there. Okay, and then we have minus x squared times W prime, which is the sum from k equal 1 to infinity of a to the k multiplied by k multiplied by x to the k minus 1. Now we have to add w, which is the sum from k equal to 0 to infinity of a sub k x to the k, and that is equal to 0. So I have decided what I'm going to do here, and I'm going to move this here. And I'm going to move this here. And so now we have that that's equal to 0. And shifting the summation index, we can see that we have k equal to 0 to infinity. And now we have replaced k with k plus 2. So we have k, whoops, write that down here. We have k plus 2. And if we replace k with k plus 2, we're now going to have k plus 1, x to the k. For our next term, we can multiply by x squared and also shift our index to k equal to 2. So we have k equal to 2 to infinity, and we have a to the k minus 1, and this is a minus, multiplied by k minus 1 x to the k, and that's what we're looking for. We need these x to the k's so that we can factor that out. Okay? And then, of course, we have our w, which is k equals 0 to infinity, a to the k sub k, x to the k power is equal to 0. So now we are going to remove the first two terms of this sum. So we're going to remove k equal to 0 and k equal to 1, and we're also going to remove the first two terms here, k equal to 0 and k equal to 1. And we're just going to take those out of our equation. Okay, so doing that, we have here, when k is 0, we have a sub 2 multiplied by 2 multiplied by 1. And when we have, and that's equal to 2a sub 2. When we have k equal to 1, we have a sub 3 multiplied by 3 multiplied by 2. And oops, and then we also have multiplied by x. So we have 6a3 multiplied by x, a sub 3x. Let's do the same thing here. When k is equal to 0, we have a naught. And when k is equal to 1, we have a sub 1 multiplied by x. Okay, so let's write those out. So these are these terms. So now we have that, this equation. Why don't I just not set this equal to 0 yet? And why don't I just say this is equal, oops, this is equal to this. And so now it is equal to, let's write those first terms. We have a naught plus 2a2. So 2a2 and a naught plus, now let's factor out x. We have a1 plus 6a3, and that's multiplied by x. So now we have the rest of our sum. So here we have plus the sum from k equal to 2, since we took out our first two terms here, and this begins at 2. So 2 to infinity, and we have a sub k plus 2 multiplied by k plus 2 times k plus 1 minus, now we're here, a sub k minus 1 multiplied by k minus 1 plus a sub k. And then all of that is multiplied by x to the k. Okay? So now we see that we must have a naught plus 2a2 has to be equal to 0. Here we have a1 plus 6a3 has to be equal to 0. And a sub k plus 2 multiplied by k plus 2 times k plus 1 minus a sub k minus 1 multiplied by k minus 1 plus a sub k also equals 0. So here we are setting, and this needs to be for k greater than or equal to 2. So we will set all of our coefficients equal to 0. And of course, that's because this is equal to 0, of course. Okay, so now we will treat a sub 1 and a naught as arbitrary constants. So we have a sub 2 is the opposite of a naught over 2. And we also have that a sub 3 is equal to the opposite of a sub 1 over 6. So we have set a naught and a sub 1 as arbitrary constants. So now we have that w of x is equal to a naught plus a1x, those are our arbitrary constants, minus, here's our a sub 2, which is the opposite of a naught over 2 multiplied by x squared, minus, and here's our a sub 3, a sub 1 over 6, x cubed, and so on and so forth. So now we can say that w of x is equal to, and let's factor that a naught out, and we have 1 minus x squared over 2 plus dot dot dot, and now we have a sub 1, and we have x minus x cubed over 6, and so on and so forth. Okay. Let's take a look at our next example. Here we're going to find a power series expansion about x equal to 0 for a general solution to the differential equation. We are going to include a general formula for the coefficients. So here we have, since x equal to 0 is an ordinary point, for the DE, we have a power series expansion of a general solution of this form. Y of x is equal to the sum n equals 0 to infinity of a sub n multiplied by x to the n power. So we also can write y prime, that's all we need for our differential equation, as the sum n equal 1 to infinity of n multiplied by a sub n x to the n minus 1. Now let's go ahead and substitute those summations into our original equation. So we have y prime is the sum n equal 1 to infinity of n a sub n x to the n minus 1 minus 2x multiplied by our y, which is n equals 0 to infinity a sub n x to the n. Okay, let's go ahead and bring our, and this is equal to 0. So now we have n equal 1 to infinity, n a sub n x to the n minus 1 minus, and let's bring that 2x into our sigma notation. So we have 2 a sub n x to the n plus 1. So keep in mind, we would like these powers of x to be the same. So what are we going to do? In this first sum, we're going to let k equal to n minus 1. And in this second sum, we are going to let k equal n plus 1, just looking at those exponents. So now we will have, I'll go ahead and write this here. So now here we have n equal to k plus 1, and we have n equal to k minus 1. So let's go ahead and write our new sum. The sum from here, k is going to be equal to 0. So the sum from k equal to 0 to infinity, and we have k plus 1 replacing our n, multiplied by a to sub k plus 1 times x to the k, which is what we wanted. So we have minus, and now when n is 0, k is 1, so we have k equal to 1. That'll kind of help there, just with our where our sum begins to infinity. And we have 2a to the k minus 1 x to the k. And that's equal to 0. So now let's remove this first term from the first summation. So when k is 0, we have a sub 1. So now we can say that that's a sub 1 plus the sum from k equal to 1 to infinity of k plus 1, a sub k plus 1 x to the k, minus the sum k equal 1 to infinity, 2a sub k minus 1 x to the k. And now we can factor that x sub k out. So we have a sub 1 plus the sum k equal 1 to infinity, and we have k plus 1 multiplied by a sub k plus 1 minus 2a sub k minus 1, all multiplied by x to the k, and that's equal to 0. So for this power series to be equal to 0, each of the coefficients must be 0. So it must be that a sub 1 is equal to 0, and k plus 1 multiplied by a sub k plus 1 minus 2 multiplied by a sub k minus 1 is equal to 0. And of course, here our k has to be greater than or equal to 1. So what we come up with now is a sub 1 equal to 0. And solving for a sub k plus 1, we have 2a sub k minus 1 divided by k plus 1. Of course, k still has to be greater than or equal to 1. Now, let's go ahead and look at this recurrence relation and see what we have here. So, as you can see, that since a sub 1 is equal to 0, we have that a sub 3 is equal to 2a sub 1 over 3, which is equal to 0. And a sub 5 is equal to 2a sub 3 over 5, which is equal to 0, and so on and so forth. So for the even coefficients, we have that for k equal to 1, we have a sub 2 is equal to 2a naught over 2. And we have when k is equal to 3, we have a sub 4 is equal to 2a sub 2 over 4. And substituting in a sub 2, we have 2 squared, which is actually going ahead and reducing this. We have 2 squared a naught divided by 2 times 4. Let's take a look at k equal to 5. We have a sub 6 is equal to 2a sub 4 over 6. And as you can see, this is 2 cubed a naught over 2 times 4 times 6. So for the pattern for the even coefficients, we have a sub 2k is equal to 2 to the k power multiplied by a naught divided by 2 times 4 all the way multiplied by 2k. I think I can make this just a tad bit smaller, and now we can simplify that as 2 to the k power times a naught divided by, and factoring out a 2 to the k, we have 1 times 2 and so forth all the way to k, and this is equal to a naught over k factorial. Okay, and of course k equal 1, 2, and so forth. Okay, so this formula is correct for k equal to 0, since 0 factorial is 1. So now we have y of x is equal to the sum from k equal to 0 to infinity of a naught divided by k factorial multiplied by x to the 2k. And of course, we can take our a naught out of that sum, k equals 0 to infinity of x squared raised to the k power all over k factorial. And as you can see, that's a naught multiplied by e to the x squared, since we recognize that sum. And of course, we have a naught is an arbitrary constant. Okay, let's go ahead and take a look at our last example. Find a power series expansion about x equal to 0 for a general solution to the differential equation, just like we did before, and we are going to find a general formula for the coefficients. Again, for w of x, we have the sum k equal to 0 to infinity of a sub k multiplied by x to the k. So we can go ahead and find our derivatives right in the middle of our equation. So let's go ahead and do that. So we know that 3xw prime is going to be equal to 3x multiplied by the sum k equal 1 to infinity of a to the k multiplied by k multiplied by x to the k minus 1. And we see that that's equal to k equal 1 to infinity of 3k a to the k x to the k. Let's also find y double prime using this y of x, and we have the sum from k equal 2 to infinity of a to the k multiplied by k, and there's that second derivative, k minus 1, x to the k minus 2. And we can actually go ahead and say, and now we can go ahead and shift our index, going ahead and adding 2 to k. We have k equal to 0 to infinity, a sub k plus 2, k plus 2, k plus 1 multiplied by x to the k. Just shift all that over just a minute. And there we have our powers of x to the k. So now we have w double prime plus 3x w prime minus w is equal to 0. So we have the sum k equals 0 to infinity of a sub k plus 2 multiplied by k plus 2, k plus 1, x to the k. Let's go ahead and substitute this term in for the 3x y prime term. We have the sum from k equal 1 to infinity of 3k a to the k, x to the k. And now we still have to subtract w, which is right here. And that's the sum k equals 0 to infinity of a sub k, x to the k. And that is equal to 0. Now we do want to remove one term. So here we're going to remove or extract k equal to 1 term, and k equal to 0 term. And we're also going to do that here so that our indexes will match. So let's go ahead and do this. When k is equal to 0, we have a sub 2 multiplied by 2, which is 2a sub 2. And when k is equal to 0 here, we have the opposite of a naught. So let's continue on, and we can say that we have the sum. Let's put those terms first. We have 2a sub 2 minus a naught plus, now we have the sum from k equal 1 to infinity of a sub k plus 2 multiplied by k plus 2, k plus 1, and let's go ahead and take that, multiplied by x to the k. And actually, since all of our terms have a sum that now begins at 1, we could go ahead and factor that x to the k out. So now we have plus 3k minus 1 multiplied by a to the k. There we go, our minus 1. And then there's our 3k, all multiplied by a sub k. And then this is multiplied by x to the k, and this is equal to 0. So now what we need to do is we need to work on our coefficients and setting every coefficient equal to 0. And let's do that right here. I'll just keep this here. And let's just go back to the way we had it. So nice. Okay. So now let's do that. We know that 2a sub 2 minus a naught is equal to 0. And also a sub k plus 2 is equal to the opposite. And then I'm just solving for a sub k sub 2 here. Okay. So if you look at that, we will have the opposite of 3k minus 1 divided by k plus 2, k plus 1, all multiplied by a sub k. And of course, k has to be greater than or equal to 1. So now the initial conditions, from our initial conditions, let's go ahead and write those down. We have that w of 0 was given to be equal to a naught, which is equal to 2. And we also have that w prime of 0, which is equal to a sub 1, was also equal to 0. So what do we have? We have now that a sub 2 is equal to a naught over 2. And that is equal to 1. So now we can compute a sub 3 is equal to a. Of course, we're going to let k equal to 1 here, so let me write that. We have a sub 3 is equal to the opposite of 3 times 1 minus 1 all over 1 plus 2, plugging in right here. 1 plus 2 multiplied by 1 plus 1, all multiplied by a sub 1, which is a negative 1/3 a sub 1, and that's going to be equal to 0. We also have, when k is equal to 2, we have a sub 4 is equal to 3 times 2, whoops, there's an opposite there, minus 1 divided by 2 plus 2 multiplied by 2 plus 1, all multiplied by a sub 2, and that's going to be equal to, if you compute that, negative 5/12. If we continue on like this, if we have k equal to 3, you will see that a sub 5 is equal to 0. And if we compute a k equal to 4, we will have a sub 6 is equal to 11 over 72, and so on and so forth. Therefore, our solution, w of x is equal to 2 plus x squared minus 5/12 x to the 4th plus 11 over 72 x to the 6th plus, and so on and so forth. And that concludes this video.